Hello everyone, today is day 41 of solving a LeetCode problem every day, and today I'm going to be solving closest binary search tree value. So given the root of a binary search tree and a target value, return the value in the BST that is closest to the target. If there are multiple answers, print the smallest. So in this specific example, we have a binary search tree, and here we have 4, 2, 5, 1, and 3. And our target is 3.7. So we want to return the node which has the value that is closest to 3.7, and the output in this case is 4. And that seems to be the only example that they're giving us. And I guess the other closest one would be, no, that would just be 4 in this case. So yeah, so we can essentially break this problem down into two parts. Part number one is how are we going to traverse this tree, and the way we're going to do that is just recursively. And the other part is maintaining a reference to, I guess, the node's value, which is closest to the target. So essentially what we're going to do is we're going to set the root node to be the closest node at the start, but then we're going to traverse throughout the tree. And within each iteration of the traversal, we're going to calculate and see if this new value is actually the value that we're looking for that's closer to target. So the first thing we're going to do is initialize our closest variable, and this is going to be an array. And the reason why I'm making it an array is because the first position at index 0 is going to store the value. And in the second position, what we're going to do is store the absolute value of the target value subtracted by the current value that we're at. And the reason why we're finding the absolute value is because we just want to find whatever, how far this value away is from the target, but we don't really care about negatives, or we don't really care whether the value is negative or positive. So we do that. The next thing we want to do is we're going to create our traversal method, and we're just going to make this within this method right here. So we're going to call it traverse, and what we're going to do is we're going to create a reference to the outside closest variable. So here we're essentially just saying we want to use the closest variable from non-locally. So we don't want to use whatever is in here, but we want to reference the one that's outside. So that's basically what's being done there. And then we have the base case, since we're doing this recursively, and we're going to check if the root is currently none. And in that case, we're going to return none. Otherwise, this is what we're going to do. So we first want to do the processing to check if the current value should be closest, and this is how we're going to do it. So we're going to first say, let's see, what should we call it? Let's say calc is equal to absolute value of target minus root.val. So essentially, so what we're doing here is the same calculation here. We want to find out the difference between our target value and our root value. Then we're going to compare it to this value right here. And if this value is smaller, it means that it's closer to our target value, which means that we want to set this current node to be our new closest node. So we're going to say if calc is less than or equal to closest at index 1, because we are storing this difference in index 1, then this is what we're going to do. We're first going to check if this calculated value is equal to the closest value. And the reason why we're going to do that is because there can be the case where, for example, the target value might be something like 4, and we have the values 3 and 5. 3 and 5 are both equal distance away from the target value. So hypothetically, they're both valid answers. However, here it tells us if there are multiple answers, print the smallest. So what we're going to do is if two values difference are equal to each other, we just want to set closest to be whatever the current less value is. So, or whatever, yeah, so whatever the smallest value is. So within here, we're going to say if root.val is less than or equal to closest. Only in that case do we want to change what the closest value is. So we're saying if the current value that we're at is less than or equal to whatever the current closest value at, or whatever the closest node is, then we want to change it in that case. Otherwise, we don't really need to do anything, so we can just skip that. We can just say else, and we can say so we're gonna say closest is equal to, or hold on, let me just make sure I'm doing the right thing here. Right, so our one case is if calc is equal to closest, which means we have two nodes that are equal distances away to our target. So otherwise, if these are not equal to each other, then we know that this calculated value is less than whatever the current value is, which is in closest, or whatever it's less than the current difference, which is stored here in closest. So in that case, we can update our closest value. So just root.val and this calculated value. And then after that, we actually perform our traversions. So we can say traverse, or our traversals. And so traverse root.left and traverse root.right. And if you're wondering what order the processing is going to be done, so we start with the root and then we go to root.left and we process the root and then go root.left. We go back, root.right. So yeah, so we're going left, we're processing left or root. Yeah, we're doing root, left, right, I believe. Anyways, I mean, the details aren't that important, but yeah, that's what's happening here. We're processing the root first, and then we're traversing to the left. Then we process the root, we go to the left again, and we keep processing till eventually we go back, and then we start traversing the right. So in the end, all you got to do is now just call the traversal function on the root, and then return the closest values. If I run this, let's see what happens. So it's accepted, and if I submit it, it's accepted too. So as for time complexity, the time complexity is going to be O of n, and the reason why it's O of n is because we're just traversing each node once. And then as for space complexity, let's see. Space complexity should just be constant since the amount of space we're using isn't determined based off whatever our input size is. So our space complexity is going to be constant. So yeah, that is my solution for the day.